Gordon. Hi, I'm Matt Mazloff. I am going to be talking today about GO-BGC for modeling and assimilation. This is a recorded presentation for the GO-BGC scientific workshop. My take-home messages are that modeling efforts desperately need GO-BGC. It's been said that a model is a hypothesis of the ocean state and how the ocean state evolves, and we only learn about the model. We can only test this hypothesis with data. We always need to hold the models accountable to the data. We need to see how well they're doing, where they're going wrong. There's three, you could boil it down to three places where GO-BGC is desperately needed by the modeling community, and one is how to validate and tune models to determine modeling error. We want to know what the state of the ocean was or is. And so we need to make map products, reanalysis, state estimates. We need data for that. We need GO-BGC. And we want to make predictions, forecasts, projections, and we need GO-BGC to initialize them. There are many ocean physical modeling and reanalysis products and efforts. This has been going on for decades, and you can learn more about them at go-oceanview.org. I don't want to talk much about the physical reanalyses, but when they started out, they were not that close to, they had lots of issues, but they've become surprisingly good. And if you look at the Ocean Reanalysis Intercomparison Project website, there's a bunch of papers archived there that talk about comparison of these reanalyses. And they are, like I said, they're becoming surprisingly good. This is a paper from Carden, Penny, and County in 2019, where they show misfits. This is the left is standard deviation of products to observations, and the right is mean difference. Oh, sorry. Left is mean, right is standard deviation. But the point here is these are four products. One's a climatology, one is a 3D VAR reanalysis, or I think it's just a nub. And we have ECHO, and then we have ORS5. ORS5 is the ECMWF effort. ECHO is the NASA effort. The point here is that when you look at the mean difference, it's less than a degree, almost everywhere. Some places where it's not, maybe in the western boundaries, or places where we expect biases because it's, I expect errors, misfits, I should say, because there's a lot of variability. The mean misfit in ECHO is highest over the rest of the ocean, but when you look at standard deviation, it's as low. The variability is being captured. I could argue that's maybe even better. And the places where the standard deviations are large, and when I say large, I still only mean, around a degree C, are in places of really high energetic variability. The physical reanalysis are getting really skillful. And similarly, there are now a whole bunch of biogeochemical modeling and forecasting reanalysis efforts underway. So it's an exciting time. However, these reanalyses will only be useful if we have data to assimilate, if we have ways to validate them, if we can confirm their uncertainty and how close they are to the real ocean. So we'll need biogeochemical Argo. We'll need GO-BGC to do this. And there was a workshop previously, the Global Biogeochemical Argo Fleet Knowledge to Action Workshop. And there are many great presentations about what's going on in some of these efforts at the link at the bottom of the screen. I recommend you check some of those out, but I'll summarize. Pierre-Yves Letron talked about what's going on with the Copernicus Earth system monitoring, where they providing forecasts and forecasts including BGC, and talked about how when they considered physical Argo, it significantly improved the solution, 20% to 60% improvement of the solution. We'll see the same with BGC Argo, maybe better, because for various reasons that I might try to touch on later, it's going to be a huge impact on these products. Example of what they're doing at Copernicus Marine Services. I recommend you check the talk out. It was excellent. And there he made the point that the main source of in situ observations for oxygen, nitrogen, chlorophyll is GO-BGC. And also the point that I made earlier, that they need GO-BGC to validate their models and to guide improvements and for data assimilation. It's vital we have this. Meanwhile, Copernicus Marine Systems, they're also doing global and regional BGC. They're doing 10-day forecasts. They're already using it to validate the models and initialize forecasts. I'm going quick, but these presentations are available. Similarly, so what they're doing is 14 to 7 days analysis and then 10 days of forecast. This is a presentation from Gianpiero Casarini, and he talked about how when you do a forecast, it's very sensitive to how well you initialize your forecast. More data leads to better forecasted models, and this is a plot of RMS difference of the forecast to surface chlorophyll as a function of time in their system. And you can see, they added satellite chlorophyll, and well, the forecast got more skillful because now the initial condition is closer to reality, and things are getting even better now down here. They just keep getting better, and as you add more BGC Argo and GO-BGC really ramps up, the forecasts are just going to continue to gain skill. Things are not just going on at Copernicus Marine Services, they're going on all over the world. This was a presentation from Shuei Masuda, talking about things going on at JAMSTech, another interesting talk. John Dunn gave examples of things going on, including, this is from his presentation, a slide talking about the NASA ECHO effort, where they did a systematic Green's function optimization of a model, a biogeochemical model, to tune it. And this is only possible because of the availability of data coming online. So yeah, I recommend you check out some of those talks. And they really demonstrate how there are plenty of users, plenty of applications, plenty of desire, plenty of demand for GO-BGC. Beyond things that were discussed there are observing system simulation experiments going on. This is a paper from David Ford, the Met Office. What is shown in this figure is if you only simulate ocean color, you get one solution. When you simulate in a simulation experiment, when you simulate also having the information that will be provided by Argo. The left is if Argo had a quarter of Argo had carried biogeochemical sensors. The right would be all of it. How much you improve that skill. So they're already simulating ocean color in this simulation experiment. They add Argo and they improve the skill in many places by 100%. So they recommend we move forward with GO-BGC as a priority. Of course, we're very interested in predictability, and there's a lot going on, a lot of literature coming out recently on potential predictability of biogeochemical properties. So this is, how well we might be able to forecast or statistically, get projections, statistical projections of how biogeochemical properties are evolving in time. And they're showing for many properties, many places, extremely long potential predictability. However, a big caveat to these works are stated from this quote from the Froelicher paper. The underlying assumption that is in their work is that they have a perfect model, and that also they have nearly perfect initial conditions. Well, we know we don't have perfect models, and we know we don't have nearly perfect initial conditions, but we can work towards perfect models and nearly perfect initial conditions as long as we have guidance from observations. We measure the real ocean with GO-BGC. We run these models, and when we don't follow the same, we don't have the same property or property evolution of the GO-BGC, we can attribute that to something, whether it's issues in how we initialize the model or how we, or is it model error itself? We can start to figure that out and improve our models and tap some of this potential predictability. Okay, back to the workshop, the recent workshop, there was a talk about assimilation of physical data. Will that help biogeochemistry? Of course, it's complicated, and sometimes yes, sometimes no. Well, when you hear no, we have to think, what does that mean? Why, what's going on? Well, this is a slide from Stefano Chiavata, taken from figures from the Park et al. 2018 paper, showing that when they did physical data assimilation, they got some spurious vertical exchange in the equator that hurt biogeochemical model. Ooh, sorry about that. So how does data assimilation work? Well, we want to come up with an analysis, a simulation of the ocean state. We call it XA. We start with the first guess, the background estimate, that's XB. And we update the background estimate informed by model data differences projected through K. So we take data, Y, the background, map them together. The H is just the mapping, just think of it just as interpolating. Map them together. We have a difference. How much do we update the state? Well, K, also known as the gain matrix, is basically a covariance matrix, cross-covariance matrix representing all space-time variables. How do we take that information of the model data difference and project it into our data simulation? Well, the difference between all the different methods you hear about is how one represents K. So objective mapping or 3D bar, K, the gain matrix, is typically prescribed from statistical inferences. For ensemble chemical filter, it's typically determined from an ensemble of model solutions. And 4D bar, it's typically determined directly from the model equations themselves. And then in machine learning, we determine it from training data statistically. Did it again. Okay, so when you hear that physical data assimilation diminishes the fit to biogeochemistry, or biogeochemistry diminishes the fit to physics, this means the covariance structure in kappa is wrong. And this is not uncommon. We've all experienced it who've tried this. Kappa is not the full true error or ocean cross covariance. You can't represent it. It's too large. So we make assumptions. We reduce the dimensionality, the degrees of freedom, and some of these assumptions lead to issues. So when you hear that, I assimilate temperature and oxygen gets worse, what that typically means is you didn't assimilate temperature correctly. There was some error in your method, and we can correct that. And this is an opportunity. This is an opportunity to develop our data assimilation methods. Similarly, your model that's representing your background estimate and your estimate itself does have errors. Again, we're making assumptions. We can't estimate the full dimensionality, the full number of degrees of freedom in the ocean. We make assumptions. We have closures. We have parameterizations in our model. And that comes into this. And if we estimate the uncertainty wrong, or we have too much model error, it'll diminish the fit, the relationships. And so, again, if we assimilate oxygen and the fit to temperature gets worse, it tells us something about the model and the whole data assimilation framework. And this is an opportunity to improve them. And I think when you hear that it matters, don't get disappointed. This is an argument for more GO-BGC. This is an argument that GO-BGC is informing our science and our efforts. Okay, so why is this such a big deal? Well, when you have assimilate temperature and salinity, you get spurious velocity. If it helps you fit to temperature and salinity, but it hurts something like oxygen, you may be getting temperature salinity right for the wrong reasons. Or maybe you don't notice that you have spurious velocities and you needed something like oxygen to infer that. And this has happened to me personally. I mean, I don't mean to pick on this assimilation effort. We have done data assimilation in the California current, and the temperature and salinity look great. We put biogeochemistry on top of it. We realized we had too much upwelling up in Northern California. And why? Because it's all about signals and noise and and how big is your temperature signal? How big is your biogeochemistry signal? Well, in the vertical, the biogeochemical gradients are huge. And this is why they're so valuable. How valuable an observation is can also be determined by how much impact it has. So when you get an observation of velocity, well, that has a white spectrum, slightly red, closer to white, and that information decays away quickly. Temperature and salinity last much, much longer. They have more memory in the system. Similarly, biogeochemistry has much more memory in the system. A measurement of oxygen lasts a long time. And when the gradients are really large in the system, it has a strong impact. So this is a line up 150 west in the tropical Pacific. So on the right, you see Hawaii. So south to north. And if you look, over the dynamic range over the ocean for temperature, it's going from 0 to 17 degrees. It's always around 34.5 in the salinity. I'm not saying that salinity is not important. When you look at oxygen, when you go from the surface where you have values of like 225, just a little into the interior where you have values near 0, that is a huge dynamic range. That is a huge gradient. And that is going to constrain your vertical velocities strongly. And it's going to be very sensitive to uncertainty or errors in your vertical velocity. And that just goes to show the power of these GO-BGC observations. I do think you can do really well with the horizontal circulation by getting temperature and salinity right. But if you want to get the vertical circulation right, GO-BGC is going to be incredibly powerful. And even if you only care about physical variables, if you want to know how much available heat content there is in the upper ocean, well, you need to know how much vertical exchange there is in the upper ocean. And oxygen tells you that. On the right is carbon, which also has a similar story where it's varying from 2000 at the surface to 2400 in the interior. These are big signals, big gradients. So Stefano Ciavatta went on to explain how the strong link between temperature and biogeochemical measurements like nitrate should help both. So when you only assimilate temperature and ignore biogeochemistry, you really break the strong T to N relationships. If you do physics and biogeochemical assimilation coupled, you can keep the relationship. But when you only assimilate temperature, you keep it, but you don't do as well as when you assimilate temperature and nitrate. So by assimilating all these together, you're getting strong, tight relationships. You're keeping strong, tight relationships. You're getting the right answer for the right reason. He also talked about how ocean, we need to consider all platforms, and there's pros and ocean color because of its great coverage. I mean, it's really great to see everywhere and to see the phasing of the blooms. However, it doesn't inform into the interior. And if your vertical exchanges are wrong, you can easily have a lot of problems with it if you don't consider the interior properly as well. So GO-BGC is really vital for that. Okay, I'm going to finish up by talking about how well we understand the ocean. And I want to give an example that if we go back to the data assimilation framework, what we're looking for is to determine the analysis, XA. And we need to do that by determining the cost function. We need a well-constrained cost function. So our goal is to minimize this model data difference, right? When we come up with XA, that should be the minimum of Y minus HXA, of course, normalized by the uncertainty. So we only, if one region is much more uncertain than the other, we don't weight them equally. So the magnitude of the cost function J, the magnitude of the model data difference or the reanalysis data difference is the likelihood that the simulation is correct, that this is the real ocean. J is determined with data, and the shape of J is something that we don't talk much about, but it's very important to consider the shape of J, because if you only have a few data points, there will be many, 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 many realizations of the ocean state that have the same cost. And so here I have a schematic of that. So here's the cost value, and here's state space. And the state space of the ocean is enormous. This is all, think of all the temperature, salinity, biogeochemical variables at every position in space and time. And what's the likelihood that that is the real ocean? Well, obviously, if it's crazy, you have a very high cost and it's not real. But if you have many, many observations, how likely your simulation is, your state is, will be well defined. A well-determined cost function minimum requires a well-observed ocean. So where we're at right now with ocean state estimation can be probed by looking at J. Does J have a tight shape where we know where we must be, or are there many locations? And so this is something that we've started looking into, and this is a figure from Verdi and Mazloff 2017, where what we did is we have the carbon flux from biogeochemical state estimate. This is the carbon flux from biogeochemical state estimate. This is another, for comparison, this is another product. This is a Landshutzer product. There are differences. There are also, this biogeochemical state estimate had a first guess. This is XA, and the first guess, the background, XB. When we difference them, we see what the adjustment is. This ranges from -4 to 4. There are some big adjustments. But let's say, how realistic is this air-sea flux estimate by BSOSI? Well, we perturbed a bunch of model parameters and reran. And so we got an ensemble of possible simulations. And then we weighted, we calculated the costs of those. How far is this air-sea flux, or how far is the PCO2 from SOCAT? So basically, the cost function was SOCAT, and how far were we from SOCAT was the likelihood that the simulation was correct for each of those ensemble members. So we estimated, we then did a standard deviation, a weighted standard deviation of the air-sea flux in each of those ensemble members from the ensemble. Sorry. We weighted each ensemble member by its cost, well, inverse cost. So very high cost, low likelihood, doesn't get much weight. We take the standard deviation of it, and that gives the uncertainty. That gives an estimation of the uncertainty. So how far could you be from the mean solution, but still have a cost that's reasonable compared to SOCAT? And we got an error of about 1 mole per meter squared per year. That's large, and the caveat is this wasn't a large ensemble. We need to do more. We need to look at this more, but it implies, considering the signal is going from -4 to 4 and the error is 1, it implies that we're still kind of at a state where the state space is not well determined. There's still many simulations that are plausible, and I think that in some places Landshutzer is probably much better than BSOSI, but in general, there's some big differences here, and they're probably plausible. If you consider the difference of SOCAT, you probably wouldn't completely rule out either of these. So we need GO-BGC and BGC Argo to constrain the ocean and to help us understand what the ocean's doing today, to understand where the errors in our models, to make map products, and to skillfully initialize forecasts and projections. Feel free to contact me if you'd like any more information on this, discuss things. Comments greatly appreciated. Thank you.